Deep beneath the surface of the Pacific Ocean, in a place where sunlight has never reached, something impossible may be happening. In complete darkness, where life is supposed to consume oxygen, a field of metallic stones may be creating it instead. The descent into the deep ocean does not feel like entering a place, it feels like leaving a system behind. By the time you reach the abyssal plain, 4, 5, sometimes 6,000 meters below the surface, you are no longer in an environment shaped by sunlight, weather, or familiar cycles. You are in a system governed almost entirely by chemistry, by slow geological processes, and yet powerful enough to define what can and cannot exist. Scattered across this uniform darkness are objects that do not belong to the idea of a passive seabed, rounded metallic nodules resting on the surface as if placed there deliberately, each one built over millions of years through the gradual accumulation of metals like manganese, iron, cobalt, and nickel, forming concentric layers around tiny cores. These are the manganese nodules of regions like the Clarion-Clipperton Zone, a vast mineral field in the eastern Pacific that has become one of the most intensely studied and contested deep-sea environments on Earth, not only because of its economic value, but because of what it might reveal about how chemistry behaves under extreme conditions. For decades, these nodules were treated as inert geological features, slow-growing archives of ocean chemistry, valuable for mining but biologically irrelevant beyond providing a surface for microorganisms to attach to. However, that assumption began to fracture when direct measurements of the surrounding water started to produce results that did not align with expectation. In an environment where no sunlight penetrates, where photosynthesis is impossible, oxygen dynamics follow a predictable rule. Oxygen is consumed, not produced. Microbial respiration, the breakdown of organic matter drifting down from the surface, and chemical oxidation processes all act as sinks, gradually reducing oxygen levels in deep water. This is not theoretical, it is one of the most stable principles in oceanography. And yet, in 2023, a research group led by Andrew Sweetman, working with the Scottish Association for Marine Science, reported something that did not fit that model. Localized increases in oxygen concentration measured directly above nodule-rich seafloor regions, increases that appeared to occur in total darkness and without any obvious biological source. Sweetman and his colleagues proposed a mechanism that shifted the entire interpretation of what these nodules might be doing. Their hypothesis was not biological, but electrochemical, rooted in the unique composition of the nodules themselves. Because each nodule is composed of multiple metal layers with slightly different chemical potentials, they argued that small voltage differences could exist across their surfaces, effectively turning each rock into a microscale electrochemical cell. In the presence of seawater, a naturally conductive electrolyte, these could drive reactions analogous to electrolysis, splitting water molecules into hydrogen and oxygen. The oxygen produced would then dissolve into the surrounding water, creating the measured increases. This process would represent a form of abiotic oxygen generation independent of sunlight, a phenomenon that the researchers informally referred to as dark oxygen. The implications of such a process are enormous because of what it represents conceptually. Oxygen production on Earth has always been framed as a light-driven process, fundamentally tied to the evolution of photosynthetic organisms billions of years ago. The Great Oxidation Event, one of the most significant transitions in Earth's history, was driven by cyanobacteria using sunlight to split water and release oxygen, transforming the atmosphere and enabling the evolution of complex life. If manganese nodules, or any mineral system, can produce oxygen without light, then the assumption that oxygen requires biology and sunlight becomes less absolute. It opens the possibility that oxygen could exist in environments previously thought to be entirely anoxic, including not just Earth's deep oceans, but potentially extraterrestrial settings as well. However, this is precisely where the controversy intensifies. Critics have pointed out that measuring small changes in oxygen concentration in deep-sea environments is extremely difficult, and that even minor calibration errors, contamination, or unaccounted-for biological activity could produce misleading results. Some researchers argue that microbially mediated processes, such as the breakdown of organic material or previously unrecognized metabolic pathways, could explain the observations without invoking electrochemical oxygen production. Others have questioned whether the electrical potentials within manganese nodules are sufficient to drive water splitting at all, given the energy requirements of electrolysis and the dissipative nature of seawater environments. This tension between possibility and doubt is what makes the phenomenon so compelling, because it exists in a space where the evidence is suggestive but not definitive, and where the consequences, if validated, would extend far beyond the immediate system. The connection to extraterrestrial environments is particularly striking, because many planetary bodies lack sunlight at the surfaces or subsurface oceans where liquid water exists. Moons such as Europa and Enceladus, for example, are believed to host vast oceans beneath thick ice shells, environments where hydrothermal activity and chemical gradients may provide energy for life. If oxygen or oxygen-like oxidants can be generated abiotically through mineral processes, then the chemical landscapes of these worlds become more complex, supporting metabolic pathways that do not rely on photosynthesis at all. Even on Mars, where surface conditions are harsh and radiation is intense, subsurface mineral interactions could, in principle, create localized chemical environments that differ significantly from the broader atmosphere. Back on Earth, the manganese nodules themselves remain silent, their growth continuing at rates so slow they are almost beyond comprehension, and yet their presence now carries a different weight. They are potential participants in a system we do not fully understand. This becomes especially relevant in the context of deep-sea mining, which is accelerating as demand for metals used in batteries and electronics continues to rise. The Clarion-Clipperton Zone, in particular, has become a focal point for industrial interest, with multiple nations and corporations exploring the feasibility of large-scale nodule extraction. If these nodules are indeed contributing to local oxygen dynamics, then their removal could have consequences that extend beyond simple habitat disruption, potentially altering chemical balances in ways that are not yet predictable. Unlike terrestrial plants or animals, manganese nodules have no place in mythology, no record in folklore, no presence in cultural memory, because they exist in a realm humans have only recently begun to explore. As the instruments continue to measure, as more data is collected, and as independent teams attempt to replicate or refute the findings, the question remains unresolved: whether the conditions for something as fundamental as oxygen can emerge not only from life, but from the quiet, persistent interactions of matter itself, operating far below the reach of sunlight, in a world that, until recently, we thought we understood. I post videos that break down how reality actually works from your brain to your body to the world around you, so if that sounds interesting, subscribe and I'll see you in the next one.